Welcome back to the Thermodynamics course. This is lecture number 9. After this lecture, we'll be 75% of the way done with the course. Today is an important lecture because we're going to be looking at one of the very important ingredients for severe thunderstorms, and that is wind shear. So our topic today is to look at vertical wind shear and how it is assessed, and that is assessed on a hodograph and also the skew-T log P. We're going to be looking at the physical processes that generate helicity. We'll start with wind shear, and one important point to make here is often when we talk about speed and directional wind shear, that it's very important that it occur in the lowest 3 kilometers of a thunderstorm with respect to developing a severe thunderstorm and a tornadic severe thunderstorm. So it's that change in wind speed and direction in the lowest 3 kilometers that's very important to look at in the thunderstorm environment. Wind shear is often the critical ingredient that is the difference between a regular thunderstorm and severe tornadic thunderstorms. Wind shear is the change in wind speed or wind direction over distance, and that distance can be in the horizontal or the vertical. The units of shear, the change in wind speed over a change in distance. So you're taking a wind speed, which can be expressed in units of meters per second, and dividing that by the distance. And in this case, it's meters. So what results from that division is that unit seconds to the -1. And that's the same units that are produced in vorticity and divergence. They all have seconds to the -1. I put this last point in here because when shear is being referred to on radar, there's a different type of interpretation to that. So when using a radar, shear is calculated as the outbound plus inbound radial velocity in knots. So you've probably heard the term gate-to-gate shear several times. That would be 2 pixels next to each other, or one has outbound and one has inbound. If they both had 30 knot wind, 30 knot outbound next to 30 knot inbound, then there would be 60 knots of shear, because you're adding the outbound plus the inbound. We're going to look at horizontal speed shear first. Horizontal speed shear is the change in wind speed over distance. And this is a horizontal distance, so we're looking at the surface or on a constant pressure surface. This shear is common along a frontal boundary and a convergence axis. This shear can induce rotation and turbulence. If the shear produces convergence near the surface, the air will rise. And on the overhead camera, we'll look at an example of horizontal speed shear. There is also directional shear too, since these wind vectors are in different directions, but we're going to focus right now on the speed shear, which is a change in wind speed over distance. To the south, we have fairly significant winds coming from the south. So we have long wind vectors here coming from the south. And we have a warm frontal boundary here. To the north of the warm frontal boundary, we have weaker winds, which are coming out of the east and southeast type direction. But you have these stronger winds here approaching weaker winds. When that situation occurs, and this is a warm front, so we're at the surface, it's going to force this air to rise. This air also is colder, so this air is more dense, so this air coming from the south is going to flow up the slope of this warm front. And since you have stronger winds moving into weaker winds also, that's going to also promote convergence along the front and lifting. So often near the warm frontal boundary is a prime area for uplift and precipitation, especially if this wind coming from the south down here has high dew points. Next, we'll look at horizontal directional shear. This is a change in wind direction over distance. This shear commonly occurs along fronts, outflow boundaries, and other mesoscale boundaries. This shear can also induce rotation and turbulence. Where air flows towards each other, convergence occurs. Low-level convergence will contribute to rising air. And on the overhead, we'll look at an example of directional shear. We saw it also in the previous example where you had different wind directions. Here you have a more significant wind direction going from one side of the boundary to another. In this situation, we have a dry line where the winds to the west of the dry line are out of the west, southwest. To the east of the dry line, the winds are out of the south and southeast. So and we're at the surface here, or near the surface. So we got the winds approaching each other from different directions. That's going to cause mass to pile up near the dry line boundary. So when you're analyzing the dry line, look to see how much convergence is occurring along the dry line. If the wind direction is about the same on each side of the dry line, then there's not going to be as much convergence, so you're not going to have as much lifting. But in a situation where you have vastly different wind directions on each side of the dry line, and especially if that dry line is progressing towards the east during the day, you'll often have strong convergence and thunderstorms can develop along that dry line, especially if this air in here has a high dew point moisture that's converging into this axis. This is known as a dry line bulge here that I drew in. The segment of wind along the dry line is not always constant. You may have a region of higher mid-level wind, and that helps surge the dry line forward more rapidly in one place than another. And that occurs, you're going to enhance your convergence. So in this region here, you would have enhanced convergence because you have stronger winds. The winds are approaching each other more quickly. You have a stronger magnitude of wind. We'll look at vertical speed shear. Vertical speed shear is a change in wind speed with height. So far we've looked at how the wind speed and direction changes at the surface or on a constant pressure surface. In this situation, we're looking at how it changes with height. Wind speed typically increases with height since surface friction slows the air closest to the Earth's surface. This vertical shear will be more dramatic when a low-level jet, shortwave, jet streak, or frontal boundary is in the vicinity of the forecast area. Vertical directional shear. This is a change in wind direction with height. If it's a clockwise turning with height, it's termed a veering wind. And if it's a counterclockwise turning with height, it's termed a backing wind. And remember, this is in the vertical. This is how the wind direction is changing in the vertical. It's a different situation if you're assessing how the wind direction is changing at the surface at a constant pressure level. You could have a situation where, like at the surface, the winds are backing over time, but as you go up with height, the winds are veering. So when you're assessing whether the winds are veering or backing, make sure that you're analyzing, is that a change with height or is that a change over time on a constant pressure surface or at the Earth's surface? The wind direction will typically change with height since friction alters the surface wind direction. Features such as low-level jet, shortwave, jet streak, or frontal boundary will cause the turning of the wind with height to be more dramatic. So if you're in a typical summertime situation where if you're in the middle of an air mass, you may not have much of directional change of wind with height. But if you have different air masses in the verticals, or there's a low pressure nearby, or frontal boundaries, you'll tend to have a more significant turning of the wind as you go up with height. The severe thunderstorm environment will often have a veering wind profile. And that veering wind profile is a clockwise turning with height. And we'll go to the overhead camera and take a look at both vertical speed shear and directional shear, our change in wind speed and direction with height. We'll start off at the surface. At the surface, we're noting that the wind is from the southeast at 17 knots. As we go up to 850 millibars, the wind speed increases to 30 knots. So we know that we have speed shear. The wind speed is increasing with height, 700 millibars up to 50 knots, 500 millibars up to 70 knots. But not only do we have the wind speeds increasing with height, the wind direction is also changing with height. It's turning in a clockwise manner with height. So at the surface here we have a southeast wind. It's turning clockwise to turn into a southwest wind at 850, and then it's turning more clockwise at 700 millibars to produce a west wind, continues that clockwise rotation to finally we get into the mid-upper levels, and we have a northwesterly wind. So that's an example of a veering wind profile. So the severe thunderstorm environment with supercells or multicell storms will often have this veering type wind profile, and as I mentioned, it's most important to assess it between the 1 and 3 kilometer level, which is about between the surface and 700 millibars, as we often see your most significant speed and directional wind shear. Look at 0 to 3 kilometer horizontal vorticity. Changes in wind direction and our wind speed over distance generate vorticity. Now we've discussed in other courses vorticity looking on the 700 millibar panel and assessing where there's positive vorticity advection, negative vorticity advection. This is actual vorticity that occurs from a turning of the wind in the lowest 0 to 3 kilometers of the troposphere. This wind direction and wind shear change over distance generates tubes of rotating air that are parallel to the Earth's surface, and this is termed horizontal vorticity. When you're looking at a 500 millibar model and you're looking at vorticity there, that's vertical vorticity. The axis of rotation is different in that situation than it is here. And we'll go to the overhead camera and we'll go over how horizontal vorticity is generated. So here's how it can be generated just with speed shear. You have the winds increasing with height from the surface to 850 millibars in this example. If we draw in an imaginary line segment here, that line segment is going to be forced to rotate over time because the top portion of this line segment is experiencing stronger winds. The bottom portion of the line segment is experiencing weaker winds. So over time, that line segment is going to rotate this way. So you're going to generate a twisting motion. Anytime you generate a twisting motion, you generate vorticity. In this situation, it's horizontal vorticity. This is the Earth's surface here, and you generate a tube of air that's parallel to the Earth's surface that's rotating in the same sense that my pen is rotating here. I have a pen and it rotates over time. So this is horizontal vorticity. If we're looking at vertical vorticity, which you look at 500 millibar chart and models to see that, the axis of rotation is different. It's straight up and down like this. So this is vertical vorticity. This is horizontal vorticity. Horizontal vorticity can also be generated with a wind direction change with height. So here we have winds that are coming from the southeast near the surface. and then up at 700 millibars, they're coming out of the southwest. So again, if we draw a line segment in there within that wind flow, it is going to be twisted over time. And the twisting of that line segment is also going to produce horizontal vorticity. So in a situation where you have speed shear, the wind speed increasing with height, and it's changing direction with height, then you have two mechanisms there to cause that rotating tubes of air near the surface, which are very important for the development of severe thunderstorms and tornadic thunderstorms. Next, we'll look at middle and upper level shear. So far, we've looked at wind shear mainly near the surface in the lowest 3 kilometers. But the middle and upper troposphere is also important when it comes to shear. Middle and upper level shear is supplied by the jet stream influence aloft and our troughing aloft. Strong upper level winds will tilt the thunderstorm updraft, and this increases the lifespan of the storm and helps the storm to be more intense. And positive vorticity advection, which is analyzed at the 500 millibar model panels and analysis chart, you look at that to see if there's a lifting motion, dynamic lifting. Positive vorticity advection aids in dynamic lifting. And we'll go to the overhead camera again and look at a thunderstorm tilting and what the process is that causes that. We're at the surface here, and we have a developing mature thunderstorm. It already has an overshooting top here. Here's the updraft region and the downdraft region. And as we go from the surface to the middle troposphere and upper troposphere, the wind speeds are increasing with height. So suppose that we have a jet streak up here in the upper troposphere. So we have very strong winds. So as this updraft rises, it's going to be pushed forward as it's rising. And the stronger the surrounding winds are, the more that updraft is going to be pushed forward. So this tilts the updraft and the downdraft in the thunderstorm. And this causes the lifespan of the storm to increase. It also makes it more severe. One reason for that is because this downdraft is displaced further away, so the gust fronts that come out of this downdraft are displaced further away, so your updraft continues to get a supply of low-level heat and moisture, which is important to keep the instability large and get the instability release, so you don't have the downdraft impeding into the updraft. And so this updraft can rise unimpeded all the way into the upper troposphere. You have these strong upper level winds, and that blow off you get from that produces the anvil high level clouds. And if you did not have the wind speeds increasing with height very much, then the thunderstorm would be more vertically stacked, and the downdraft would fall into the updraft, and the storm lifespan would be less, and the intensity of the storm would be less. Now we're going to look at how the wind speeds increase, how you assess the wind speeds aloft, and also to look at 500 millibars and where to look for PVA and troughing. In this first image here, we have 300 millibars. And you will notice where the stronger winds are by noticing where the height contours are packed closer together. So in this region here, over East Texas, over Arkansas, Louisiana, and Mississippi, up into Missouri, the height contours are closer together, the wind vectors are longer. So if a thunderstorm develops in this region here, it's going to be tilted more significantly than if the thunderstorm developed out over here in Georgia, Tennessee, Alabama. The wind speeds here are weaker, and you're being influenced by some ridging here too, so the environment here is not as favorable for severe thunderstorms as it is in here, where you have those strong upper level winds rotating around this trough here. and you look at 500 millibars to assess positive vorticity advection. If you have a thunderstorm, the positive vorticity advection is going to force the lifting even more. There's going to be more lifting, and in some cases you need the positive vorticity advection to generate the thunderstorm in the first place, since positive vorticity advection is a lifting mechanism. So if there's some type of capping inversion, fairly strong capping inversion, if PVA moves over, the lifting from that can break the cap and produce the thunderstorms. Or if thunderstorms are already occurring, it'll make the thunderstorm outbreak even more significant. The positive vorticity advection occurs downstream from the highest values of vorticity. The highest values are in this yellow color here, and it's going to be downstream from that where those higher values are approaching. Notice you have the wind vectors flowing through the vorticity area, so it's in this region here, the downstream region that's experiencing positive vorticity advection. The vorticity is increasing over time. So you have divergence aloft occurring in this region, forcing the air to rise even more. So this would be a prime region for if a thunderstorm developed in this region. We saw that there's strong upper level winds here, even at 500 millibars. The winds are fairly significant in this region, and there's positive vorticity advection. You got several ingredients there that aid in severe thunderstorms. So, summarizing the thunderstorm lifespan and intensity. Wind shear increases the lifespan and intensity of a thunderstorm and helps initiate the development of new thunderstorms. Two ways the lifespan intensity is increased is one, by the updraft and downdraft are tilted and thus do not impede each other. Two, the gust front does not advance too far from the storm, ensuring continued supply of convection or inflow, warm moist air, a continued supply of warm moist air into the updraft of the thunderstorm. Next, we're going to look at the hodograph and what exactly that is and how that's used to help forecast what the storm form is going to look like for that day. The hodograph, it's a display that shows the change in wind direction and wind speed with height. It's used to help determine the wind shear environment, since this plays a role in the storm type. The hodograph display. These are available online. Sometimes they'll come with the SKU-T log P diagram, and other times there's other websites where you can get just the hodograph itself. There's some software, meteorology software available too, where you can look at the hodograph. The hodograph is composed of speed rings, and it has a reversed meteorology compass. The wind vectors point toward the direction the wind is coming from in degrees. And after these wind vectors are drawn in, the tips of the wind vectors are connected to each other to produce the hodograph output that you'll commonly see when you pull up a hodograph. On the overhead camera, we'll take a look at the basic features of the hodograph. It has a center point here, and the wind speed increases as you go away from that center point. And there'll be rings of wind, and those rings will be labeled with the wind speed. The wind speed will always increase with distance away from the center. There's different units that may be used. Some of them will use meters per second, and some will use knots. Those are the two most common units that you'll run across. And it has this reversed meteorology compass, where 0 degrees is at the bottom, 180 at the top, 270 to the right, and 90 degrees towards the left. And I'll show here in a minute that the wind vector is drawn toward the degree that the wind is coming from. So we draw it this way to get a bird's eye view perspective of what the storm is seeing, what wind direction the storm is experiencing. And we'll look at an example now of plotting a hodograph. We have some data down here. We have a surface wind from the southeast at 15 knots. And the southeast wind is coming from 135 degrees. At 900 millibars, the wind is south-southeast at 22 knots. The south-southeast wind is 160 degrees. 800 millibars, a south wind, 32 knots, 180 degrees. And then finally, 700 millibar wind south-southwest, which is 200 degrees at 35 knots. And we're going to plot each one of these with a wind vector starting from the surface. We have our speed rings on here, and these are labeled in knots. So this first ring is 20, and this outer ring is 40 knots. And we have our degrees labeled on there. So the first wind vector that we want to draw is the wind pointing toward 135 degrees at 15 knots. So 15 knots is going to be 75% of the way from the center to this first outer ring. And the wind is coming from the southeast or towards 135 degrees. So we're going to put a dot in about this position there. So that represents our point on the hodograph, 135 degrees. 135 degrees is in between 90 and 180. And it's at 15 knots. So we can draw our wind vector now. So I'll draw an arrow in there starting from the center with the tip of the arrow ending at where that dot is there. So that's our first point that we've plotted. Now we'll plot 900 millibars. That's south-southeast at 22 knots. So that's a little bit greater than this first speed ring here. And the wind is flowing towards 160 degrees on our diagram, or from the south-southeast. So we'll put another dot in this position here, and we'll draw another vector starting from the center with the tip of the vector ending at our dot there. So there's our second vector representing 900 millibars. We can label these also for surface and 900. So two more to do. We got 800 millibars is from the south at 32 knots. So 32 is going to be about in between these two speed rings, but a little bit closer to 40. So we'll put it in about this position here. This is 800 millibars, and the vector will be right on this 180 degree line with the end of the vector on our dot there. And then lastly, we have 700 millibars, which is a wind from the south-southwest at 35 knots. So you've almost made it to 40, but not quite. So it's coming from the south-southwest, 200 degrees, so it'll be about in this position here. That'll be our 700 millibar. And we'll also draw another wind vector. Now when you go online or use software to look at the display, you're not going to see these vectors on there. They take the vectors off of there and just leave the dots, the endpoints. And then what is done is that those endpoint dots are connected to each other. So I'm going to connect each one of these with a black pin here. And after they're connected to each other, this is what you would see on the computer. You would see this curving line segment representing how the wind speed and direction changes with height. In this case, we went from the surface to 700 millibars. Other hodograph displays may go up higher, may go up to 500 or 200 millibars, or you may be able to pick exactly what level that you want to see the wind from. But as I mentioned before, it's most critical that you have that wind speed and direction change within the lowest 3 kilometers. So the surface is 700 millibars. This is the lowest 3 kilometers, showing that you do have some speed shear and a little bit of directional shear also. We'll next look at different storm forms. When a thunderstorm develops, the shear environment is going to influence what type of storm is going to be listed there. If the shear is too intense for the updraft, then you'll have a sheared apart convection and the thunderstorm actually won't fully develop. Or you could have a typical air mass type thunderstorm, or you could have multi-cell thunderstorms. Multi-cell thunderstorms can be non-severe or nearly severe, or they can be very severe thunderstorms. And then also the supercell thunderstorm. So we'll go through each of these and how the hodograph looks on each one. We'll start with sheared apart convection. This occurs when wind shear is very strong, but instability is relatively weak. The strong wind shear tears the convection apart before it can develop into a thunderstorm. So if you have weak cape, let's say the cape is only 200 joules per kilogram, but you have very strong speed shear with height, then that developing updraft will be tilted so much that it'll tear apart. If it tilts too much, it'll tear apart. Next, we'll look at the typical thunderstorm. It's also known as a non-severe thunderstorm, air mass thunderstorm, or garden variety thunderstorm. Generally develop in a weakly sheared environment with weak to moderate instability, and they have fairly short lifespans because that downdraft falls so close to the updraft that it cuts the updraft off and weakens it. And you also have a lot of precipitation falling into the updraft, and that weakens it. And the cape is not very high also, so the updraft to begin with isn't that intense. Here is an example of a hodograph showing weak shear. And what I want to point out here is that you have the speed rings here going from 20 knots up to 40 knots up to 80. And you notice as you go with height, here's the first one at the surface, as you go with height in the troposphere, the wind speed doesn't change that much. You never get a very fast wind speed. In fact, as you go up, let's say that this is a 500 millibar level. Let's say we're going from the surface to 500 millibars. Up at 500 millibars here, you only have a wind speed that's only around 10 to 15 knots. That's very weak wind. And the wind direction doesn't change that much either. So you got weak directional shear, weak speed shear. And I picked situations where I saw thunderstorms developing, whether they be air mass thunderstorms or multicells or supercells, and then saved a hodograph according to what the model prediction was around the time that that convection occurred. This first example is a weak shear profile during Florida thunderstorms. And here, this is starting at the surface. This outer ring here, which is labeled 10, is in meters per second. And our cape in this situation was about 600 joules per kilogram. So the cape was not all that impressive. So your instability, although you have instability, it's not too impressive. The wind shear profile is also not impressive. This is going from the surface up to 2 kilometers. Going from the surface up to 2 kilometers, by the time you got to 2 kilometers, the wind speed was just about 0. The lower and mid levels of the storm environment had very little wind. And even these wind speeds here are fairly light, all less than 10 meters per second. So a thunderstorm developing in this environment doesn't have a very intense updraft, and it's not going to be influenced much with a change in wind direction or wind speed with height. So this is a typical situation for air mass, garden variety type thunderstorm. And an important point here to make about even these typical thunderstorms is that they can kill and cause significant damage. Even though flash flooding and lightning are not part of the definition of a severe thunderstorm, these events are the top 2 storm killers. So if you have a storm that's producing some cloud-to-ground lightning, especially it's producing a lot of lightning strikes, that can be a significant killer. And also in these thunderstorms, since the shear environment is weak, they're often slow-moving. And if the cape is high enough and the updraft strong enough, you can have very heavy rain over the same region for a significant period of time, and that can produce flash flooding. So even though when you're looking at the skew-T and the hodograph, the environment doesn't look all that impressive, these typical thunderstorms are often the storms that can have a significant influence on killing. Next, we'll look at non-severe multi-cell thunderstorms. Multi-cells forming along a common lifting mechanism are termed an MCS, a mesoscale convective system. Generally develop in an environment between weak and moderate wind shear. Instability is weak to moderate. These develop into lines or pockets of storms. Convective wind gusts are generally less than 58 miles per hour and hail size less than 3/4 of an inch, so non-severe type storm. Multi-cells can also be severe. If the wind shear environment is more significant, the instability is more intense, or a combination of both, then they can become severe. Also, dry air aloft ingested into the storms can produce enhanced surface convective wind gusts. Strong updraft can produce large hail. Combining a significant wind shear and instability can also produce tornadoes. Here is an example of a hodograph that has a strong speed shear but a fairly weak directional shear. And they'll often refer to this as a straight line hodograph, although it may not be a perfectly straight line, although some segments of it can be almost fairly linear. So even though it's called a straight line hodograph, even though it's fairly straight here, you do have some change in wind direction with height. And in a straight line hodograph, you'll often have a strong speed shear where the wind speed is increasing significantly with height. So this is our surface here, where we have about a 20-knot wind. And as we go up into the upper troposphere, we got 60 to 80 knot winds. So we have an environment here where if a thunderstorm developed, it is definitely going to be tilted, and that's going to give it a longer lifespan and also increases the risk of multi-cell type thunderstorms. So you have a thunderstorm develop, it puts down an outflow boundary, which develops another storm. That storm develops, produces another outflow boundary, and you get this continued renewed convection that occurs. Here is an example of when there was multi-cell thunderstorms and I saved a hodograph in that environment. You can see the straight line influence here when you have that wind speed increasing with height. And you have some directional shear here too, although the directional shear could definitely be more impressive than it is. You definitely have some significant speed shear. Another thing to keep in mind is that this is a model output and it's at one point in time for one place. So surrounding locations and at different time periods, this profile could look more impressive. The CAPE in this situation was almost 1,400 joules per kilogram. So we have much more instability than we had in that Florida thunderstorm situation. So we have a much better shear profile than in that Florida situation, and the instability is larger too. So you expect a more significant thunderstorm event in this type situation. The storms would be more likely to be severe. Next, we'll look at the supercell thunderstorm. These are intense single-cell storms. Generally, both strong speed shear and strong directional shear are present. Moderate and strong instability will also be present. Can produce violent tornadoes, severe wind damage, and severe hail damage. High convective wind gusts be greater than 58 miles per hour with 3/4 inch hail or greater. And this is how this looks on an idealized hodograph, where not only do you have the straight line hodograph in there, in the lower troposphere you have the significant turning of the wind with height. Remember I mentioned that it's in the lowest 3 kilometers where the wind shear is most important to assess. So if you're going from the surface up to 3 kilometers, we have a significant change in the wind direction here with height. And also the wind speed is increasing significantly with height. So it has that line segment, but it definitely has that turning of the wind with height there also. And here's an example of a situation where there were severe thunderstorms, and I saved a hodograph from that situation. In this situation, the CAPE value was 2,000 joules per kilogram, so you have fairly high CAPE. And we have a significant turning of the winds with height. Or here at the surface, we got winds coming out of the east, and then as you go with height, they turn to coming out of the southeast, and then out of the south, and then the winds come out of the southwest, and you go up higher, and the winds are coming out of the west. So the wind direction becomes 180 degrees difference as you go up with height. So very significant directional change in the wind with height in this situation. And this goes from 0 to 5 kilometers. So the 0 to 3 kilometer would be in here. So between the surface and 3 kilometers, a big turning of that wind with height, and you have high instability. So this was a favorable situation for supercells, and supercells developed. Some other considerations. Storms can produce severe convective wind gusts without the aid of wind shear if dry air is ingested into the storm aloft. Evaporation cooling produces a more negatively buoyant downdraft. Mesoscale influence can significantly enhance wind shear and instability. Thus, severe storms and tornadoes occur when the synoptic wind shear and instability environments do not initially look impressive. So remember that, as I mentioned before, when you're looking at a hodograph, you're only looking at one point in time at one location. Surrounding locations are in different time frames. The shear and instability profiles can significantly change, and they will significantly change during the day. Daytime heating is going to influence the instability, and the wind shear can also change significantly during the day. Next, we're going to go through different index values that have shear information within them. You'll run across these when you're looking at your weather data, when you're assessing a thunderstorm situation. 0 to 3 kilometer directional shear, speed shear, and helicity. We'll look at the bulk Richardson number, the energy helicity index, and then finally the sweat index. All these incorporate some type of shear information. Some of them add additional information such as instability. 0 to 3 kilometer directional shear. If this is greater than 70 degrees, it's considered very significant. Storm relative directional shear. This is the directional shear experienced by the storm. And this term, storm relative, you'll come across that a lot. So I want to go over that on the overhead camera so you know what that storm relative means. As an example, we'll look at car relative wind. Suppose that you're in an automobile and you're going at 50 miles per hour. So that's your car motion. You look at what speed you're going, it says you're going 50 miles per hour. But suppose you're going into the wind and the wind is coming at you at 50 miles per hour. If you put your hand out the window, you would not feel the 50 mile per hour wind that your car says it's going, but you would actually feel 100 mile per hour wind if you put your hand out of the car. because these winds, your car is going into the wind that enhances the wind speed. And the opposite situation, your car is still going 50 miles per hour, but the wind is going the other way at 50 miles per hour. So instead of going into the wind is trying to travel away from you. In this situation, you'd have a 0 mile per hour car relative wind. The wind speeds would cancel each other out, and if you put your hand out the window, you would not feel much wind at all, assuming that the wind was a constant 50 miles per hour and your car was a constant 50 miles per hour and they were moving away from each other. So that's car relative wind. The same thing applies when you're looking at a storm. Instead of a car, you're looking at what it is from the thunderstorm's perspective. Storm relative wind. So suppose that the surface wind, we'll call this the environmental wind. We have wind that's from out of the south or south-southwest at 15 knots. So that's what the stations are reporting. Let's say we have stations scattered out here, and they're reporting about a 15-knot wind. Well, we have a thunderstorm, and it's moving in a different direction than the low-level winds are. This is the surface wind that we're looking at here. The thunderstorm is moving from a different direction. The thunderstorm is moving from the northwest. So there's a component of that thunderstorm moving into the wind. So the wind that storm is going to experience is going to be much higher than the 15-knot environmental wind. And you may think, well, why does a storm move at a different direction from the surface wind? This can happen, and often happens when you have significant wind shear, especially directional shear with height. If the mid and upper levels of the thunderstorm have winds out of the west and northwest, that's going to have an influence on the storm motion. The storm is going to tend to move at the average of the winds that the storm environment is in. So the winds, although they're from